Okay, let's put it all together with hypothesis testing from beginning to end. We're going to apply the hypothesis testing steps that we've been talking about this whole semester. So we're going to establish hypotheses to start with. We're going to talk about our critical boundaries. We're going to calculate our F statistic, and then we'll make a decision. These are all things you've done before. So this is the data that we're going to be working with, and this is data that we've used earlier in other videos where we pretend that there's 3 different temperatures in 3 different rooms, and we're looking for performance on some measure. So one room was 50 degrees, one room was 70, and one room was 90 degrees. So here are the individual scores for each treatment group. And this is the treatment total. So let's think about what treatment total is. It's adding up the values of all of these scores. So 3 plus 1 is 4, plus 1 is 5, 4, 7, 13, 16, 20. So the T is the total of these numbers added up, not the count of them. The count of them is the N. So we have 5 in each group. That's how many scores we have, but the treatment total is adding up the values, right? For each group, I've calculated the sums of squares, so you don't have to worry about that. So for each group, group 1 has the sums of squares of 6, group 2, 6, and group 3 has the sums of squares of 4. Again, the N for each group is there. And then we also have the mean for each group. The mean for group 1 was 1, the mean for group 2 is 4, and the mean for group 3 is 1. And we want to know if there's a significant treatment effect. In other words, is there a significant difference between at least 2 of these groups? I'm going to wrap up by just saying what else we need to be able to do our Anova. We need to have the sum of the squared scores. Again, that's for our sums of squares total calculation. This is sums of squares within, but we need the sums of squares total. And we're going to use that computational formula. We need the grand total of the treatment scores. That's for that sums of squares total calculation. Our total N as well, and then the number of categories that we have. So let's start with our hypotheses. So the way that we set our hypotheses in an Anova is the null hypothesis is that the groups are equal, that the means of the groups are equal. The mean of group 1 is equal to group 2 is equal to group 3. And the alternative hypothesis is that the means of these groups are not equal, that there's somewhere in there there's an inequality. So that's the hypotheses. We need to set our critical boundaries, and let's set it at 0.05. Why not? Our degrees of freedom, I'm going to be filling you in on the degrees of freedom now, although it's easier once you've done the calculation to figure out the degrees of freedom. The degrees of freedom for this study are going to be 2 and 12. You'll see that in a minute. And if you look at degrees of freedom 2 in the numerator and 12 in the denominator on your F table, you'll see a critical value of 3.88. So the F that we calculate needs to exceed 3.88. So coming on back, let's get ready to calculate our sums of squares. And you may want to pause the video and write down some of these things. In particular, write down the 3 different sums of squares within, and the information here on the right is very helpful for sums of squares. Let's start. For the sums of squares total, I've entered in some of the information from the last slide. So we knew that the sum of the squared scores was 106. The G, our grand total of the treatment scores, was 30. So in our computational formula for the sums of squares, we take 30 squared divided by the N of 15. So let's start with everything on this side first. We have 30 squared, which is 900, divided by 15, and that gives us 60. So our sums of squares total are 106 minus 60, which is 46. All right, we've got that. The sums of squares within, if you look back on the information, we had 6 in one group and 6 in another group and 4 in the last group. So our sums of squares within is 16. And as a reminder, we could do a formula to figure out the sums of squares between, but it's kind of complicated. So what we can simply do is take our sums of squares total minus our sums of squares within, and that will give us our sums of squares between of 30. So here's a summary of what we just did with the formula for the sums of squares total and how we calculated between and within. The next thing we need to do is we need to figure out the degrees of freedom. So let's do that. The degrees of freedom total, as you will recall, is n minus 1. And we have a total number of participants of 15. So 15 minus 1 is a degrees of freedom total of 14. My degrees of freedom between are my number of groups, or my number of categories or classes, minus 1. So we have 3 different treatment groups, right? So 3 minus 1 gives us a degrees of freedom between of 2. And the degrees of freedom within is basically the n minus 1 for each group. Each group has 5 participants, so n minus 1 is 4. So 4 plus 4 plus 4 gives us a degrees of freedom within of 12, and that matches what I showed you earlier, that our degrees of freedom when we look at the F table are going to be 2 and 12. All right. And here's a summary of that information as well. Now we have our sums of squares, we have our degrees of freedom, we have everything we need to find our mean squares. Remember that our mean squares is simply found by taking the sums of squares divided by the degrees of freedom. It's a variance calculation. So let's figure the mean squares between and the mean squares within. So for the mean squares between, we just take 30 divided by 2, and that gives us a mean squares between of 15. Our mean squares within is taking 16 divided by 12, and that gives us a mean squares within of 1.33. Now we have both parts of the ratio to figure out the F statistic. And here's just a quick summary of what we just did. So now we need to calculate the F ratio. And basically what we're doing is we're taking those mean squares between and dividing it by the mean squares within. 15 divided by 1.33. And what we end up with is an F statistic of 11.28. We report this as F with degrees of freedom 2 and 12 is equal to 11.28. And here it is in our Anova table. Our Anova table is complete, and now we just need to make a decision. So the decision that we make is that we are going to reject the null hypothesis. Remember, our critical value was 3 point something. Our F is 11 point something. So we reject the null hypothesis that says that there are no differences between the means. We say there are differences between the means, at least 2 of the means. So the way that we would say this in our words is the difference between treatments is 11 times bigger than would be expected as if there was no treatment effect. Remember, if there's no treatment effect, the F would be 1. But we could say that, in fact, there's 11 times a larger difference. The difference between treatments is 11 times larger than would be expected as if the null hypothesis were true. If we were going to say this using our old language that we've been using, we could do that too. We just say we reject the null hypothesis. The difference between the treatments is, or the means of the treatments are significantly different. Easy for me to say. There you go. So that is how we do hypothesis testing with Anova. And when we look for statistical significance, we say that our observed difference is unlikely to have occurred by chance. There's a low probability. And this happens when we have a large F score, but it says nothing about how big the effect was. And so what we're going to do next is we're going to talk about effect size with Anova.